So take a look here at a little bit more advanced probability. And we're going to start with what's called conditional probability. So here's a chart on the gender versus maybe some goals that certain people have in school, maybe, right? They're focused in school. So we got guys and girls, and then they're either focused on their grades, their social life, or sports. So apparently this is a school, no arts allowed. So obviously this isn't givens. So as we start looking at it, we can start to use these tables. One to find the probability of a girl. So if we're looking for the probability, we randomly select a girl from the school. Well, that would be this 251, right? That's the total number of girls over the 478, or 0.525. All right, if we want to do a girl and their focus is a social life, well, here the and isn't necessarily multiplying because we have this table. We can see there are 91 girls that are focused on their social life. So that's 91 out of the 478, or about 19%. We go, what's the probability we randomly select a student that's focused on sports? So here we go to total of sports over total of all students, and that's slightly under 19%. So the next one, it's a little bit different look at this because all of a sudden we got this idea of given that, right? And this is what a conditional probability is, right? Up at the top, you might not have noticed, but conditional probability, a lot of times if you start seeing the terms given that, or you might see the word if, right? Sports, if we know that we picked a girl. So now all of a sudden, we know something. We know that we're picking from girls. So we're just going to focus in on this particular line. So there are 30 girls focused on sports out of the 251 girls. So when we're talking about conditional probabilities, we're going to basically change the denominator. All right, one more look at it. Girl given that one plays sports. So this time, and I'll do a slightly different color. This time we know that we're picking out of the people that enjoy sports. And so there are 30 out of this group that are girls. So 30 out of the 90, or about 1/3. So the idea with this conditional probability, the probability of B given that A has occurred. So you see that vertical line, that basically means given that, or if. So that's a conditional probability. And the formula for us, it will be the probability of A and B over the probability of A, right? So here it's important to note, and doesn't mean multiply here. Typically, what we're going to end up with is a chart or somewhere within the context of the problem. Let me finish this before I forget my thought here. All right, and doesn't mean multiply in a conditional setting. I'll put a bunch of exclamation points. So here, for example, sports, given that it's a girl. So we need the probability of sports and girl over the probability of girl. Notice that the second part of the conditional is always what goes into the denominator, right? I kind of almost pretend like that's a division symbol for just a minute. So it's a probability of both, right? Another way to think about this at the top, the probability of both divided by the probability of the second one. So probability of sports and girl. So we go in here, here's sports and girl. That would be, there are 30 of those over the probability of a girl. Well, that's out of the 251. So 30 out of 251, which I wrote right over the top of where it goes, but 0.119. So before moving forward, I'm going to get this idea of disjoint or mutually exclusive. This is the exact same thing, depending upon which text you come in contact with, whether you're looking at different books or different websites. Some people say disjoint, some say mutually exclusive. Either way, it's events that have no outcomes in common. So how this works. Let's say that you're looking for a house. So some houses have garages, some have pools, some have both. So here's the idea. This is where they would have both, right? This would be only a garage on this side, and this would be houses with only a pool. Right? Some houses have a pool without a garage, some have a garage without a pool, some have both. So this would be an example of not disjoint. They have events in common. They are not mutually exclusive. Here, the color of traffic light, or the traffic light on an intersection, there is no overlap, right? So these things are disjoint, aka they're also mutually exclusive. So if they're not disjoint, we still have the word or, and or still means add, right? Or still means add. However, you have to subtract the overlap. So what it looks like, set A is 1, 2, and 3. Set B is 3, 4, and 5. So there they are. 3 has the overlap. So if we want to talk about something that's in A or B, well, if we add A plus B, we'd end up with 1, 2, and 3. We add in B, 3, 4, and 5. But we don't want to double count 3, so we'll take it back out. So really, the idea, or still means add, but you have to be aware if there's an overlap, you have to subtract the overlap. And that's basically just so you don't count it twice. So let's look at a problem with this. Police report 78% of drivers stopped on suspicion of drunk driving are given a breath test, 36 blood tests, 22% both. So we'll do breath test, blood test, and we can see we have a both setting. So this is not mutually exclusive. These things are not disjoint. And what we need to realize, when it says 78% are given a breath test, that includes those that are given both. So this 36% be all in the blood test. So 22% do both. And some quick math would tell us, right, if we want to do the probability of blood or breath, that's probability of breath plus the probability of blood minus both. So the probability that someone is given a breath or blood test would be about 92%. Now, let's take a quick second, right? We just saw this. So 78% of all drivers are given a breath test. So some are given both. We do some quick math and we realize all of a sudden that 56% are only given a breath test and 14% are only given a blood test. So here's another way to approach this breath or blood. You could do only breath plus only blood plus both. And then you don't have to worry about the overlap. But again, we've already kind of accounted for the overlap by figuring out what these only values are. Now, what's the probability they're given one test or the other but not both? Well, that would be blood only, right, for number 1, plus breath only. That'd be 0.70. What's the probability they're given neither test? Well, we just saw blood or breath previously, right, was 92%, right? Blood or breath. The previous couple slides, we saw that was 92%, which means there's 8% of people that didn't, right? So 1 minus the probability of those that are tested. 92% of people were tested, so 1 minus 0.92 equals 0.08. So 8% of the people were given no test at all. What's the probability a randomly selected driver who has been given a blood test will also be given a breath test? So here all of a sudden we know something about them. We know they have been given a blood test already. So really we're looking at what's the probability out of this group of people we get somebody that is also over here. So in other words, we're kind of ignoring all of those folks there. So here's a conditional probability of A and B over A. So again, for us, we're looking for the probability of a breath test given a blood test, right? That P is kind of weak. So if we want to break this down, I see I've got A's and B's there. So this would turn into breath and blood over the probability of just blood. Remember, the second one is the one that goes in the denominator here. And so that's where those numbers are coming from, right? 22% were given both. 36% of people were given a blood test, right? Its total was 36. So that's where that number is coming from. Do the calculations, you end up with 61% of those that have been given a blood test are also given a breath test. Right. Another way to approach this is to make a table, and it kind of makes it a little bit easier. Most people they enjoy the table a little bit better anyway. So here you basically set up this kind of 3x3 table where you have yes, no, total going on the top and on the side. And the one thing to realize, the bottom left corner will always be 1, right? Probability is always sum to 1. I like to kind of highlight the total row and total column. So 36% of people you see are given a blood test. So that's the total number of blood tests. That's where that's coming from. 78% is a total for breath tests. That's what's going there. And then you have this 22% get both. So that 22% is going to go with yes to breath and yes to blood. And it's at this point that rows and columns should start to sum up. So in other words, right, the missing piece there, that's 14%. Now we think if 78% of people were given a breath test, that means 22% were not. 36% of people were given a blood test, which means that 64% were not. Here, now just look at column totals. So we're missing 8% there, and then this would be 56%. So now all of a sudden, remember before we saw the probability of none was 8%? Well, it's easily seen in that table, right? So if you allow me, I'll erase all my marks so you can kind of see what's behind here. If we wanted to do a conditional probability, what's the probability of blood given a breath test? So if they've been given a breath test, what's the probability they also get a blood test? Well, now we just go straight to the table, breath and blood. Well, that'd be yes and yes, right? That's a probability of both. So that's 22%. And then over the probability of a breath test. So the total for breath test is 0.78. So 0.22 divided by 0.78, 0.282. So one more example, 56% of all American workers have a retirement plan, 68% health insurance, 49% both. So again, we'll go to our totals, right? One always goes in that bottom right-hand corner. 68% was the total for health insurance, right? Total health insurance. 49% have both. That'll go there. And then just work the math out, and you can fill in the rest of the table. So what's the probability somebody has neither plan? Well, that's sitting right there. No and no, 0.25. What's the probability they have a health plan if we know they have a retirement plan? Again, let's turn that into conditional. Probability they have health given a retirement plan. And once we have that conditional written, we can then write that conditional all the way out, right? Turn it into this situation. So that would be health and retirement. Sorry, that's a terrible H. Over, right? Retirement's the second piece. Now that we've got that, health and retirement, well, that was the 0.49. Over the probability they have a retirement plan is the 0.56. And then 0.49 divided by 0.56 is 0.875. So there's about just slightly under 88% chance that if we pick someone that definitely has a retirement plan, they probably also have a health insurance plan.